Hey everybody, there's one more math thing that I want to cover because it's going to come up again and again and it's actually really useful. And that's called parametric equations. So luckily, although parametric equations gets really complicated, and you can even think this might be review, from your math class. You should have learned this somewhere else by now. It's actually not hard with graphics. And so, like with the other math, I'm going to focus first on explaining what it is from the intuition point of view, and then we'll go through an example of how it works math-wise. But this is how math works for me. I've always been pretty good at math, and I think the reason is because I didn't focus on the formulas. We can always look those up. Focus on the intuition. What does this mean? If you can figure that out, then you can always know how to use it and look up what you need. So what we want to do for parametric equations is we want to redefine any formula we have, and the formulas we're going to use in graphics are like lines, circles, that kind of thing. So redefine an equation in terms of some new parameter. So new variable that wasn't there before. That's why it's called parametric. It's a new parameter. We typically call this t. Helps if I can spell. All right. Typically called t. We call it t. I don't know why. For curves and lines, it's basically what you're going to use it for in graphics. So curves and lines. So instead of having some function where we have y as a function of x, I give it an x, I get a y, right? Like we might be familiar with this goodie, y equals mx plus b, y is the slope times x plus y offset. The problem here is that this relates x and y together, but it can be kind of hard to use in many circumstances. Instead, sometimes it's useful to think about as we progress along some trajectory or some curve. So I'm just going to draw some random curve here. This is just random curve. And wouldn't it be nice if we could start here and end there as we went along our function? If we have f of x and y, this gets complicated fast. Here we have multiple x points, multiple y points for one x. So we're going to have some roots in there. It gets like a mess real quick. It's too complicated. So sometimes it's useful to look at these things differently. So instead of defining what x and y related to, we define the functions as progress along the curve. Instead, define the function as progress along the curve. Okay, so what we want to do is something like this. I'm going to say, well, here's the beginning of my curve. I'm going to call that t of 0. That's where I start my curve. And I'm going to go along, and here's the end of my curve. When I get to t of 1, I want to be there. And in the middle, I'm going to guess at the middle. It looks like I'm at the middle. At t half there. So I want t to bring, if I increase t, I want some function where t of 0 gives me the beginning, t of 1 gives me the end, and I can move along that curve just by increasing my t. So as t goes from 0 to 1, we have two functions here. That give us x and y. So instead of having y equals mx plus b, or y equals, in this case, some function of x, some complicated function with roots and squares, I want x equals some function of t, and I want y to equal some other function of t. Okay, so I give it a t, it gives me an x, it gives me a y, bam, I can plot that. So let's look at what this might look like in practice, okay? But the intuition I'm hopeful for is that the idea you have this parameter, it goes from 0 to 1, we get some functions, we give it a t, it gives us the x and the y, okay? So let's parameterize a line. So parametric form for a line. And I'm going to put segment in here because really in graphics we don't work with lines, we work with line segments, right? So let's see what this might look like. So I'm going to graph over here. I have point 1, I have point 2, and these 2 points determine the ends of my line segment. Okay, so classically we have y equals mx plus b, but instead of working on that and figuring out the slope, we can do that. That's not hard. Instead of doing that, let's parameterize. Parameterize this line. We want t of 0 to be the start of the segment, and we want t of 1 to be the end of the segment. Okay, so let's look at that. So the first thing I'm going to do, let's fill this line in. I'm going to make a vector L, which equals P2 minus P1. So I take P2 minus P1, it'll give me this vector L from P1 to P2. So let's create this vector L. It's P2 minus P1. And then I'm going to make a function called L of t. And what that is it's going to start at P1. So I'm going to start at P1, and then I'm going to add t times this vector L. Okay? So I'm going to start at P1. If t is 0 then, so if t is 0, then L goes away, then we just have P1, which is what we want. We want t of 0 to be here. If t is 1, then what we get is P1 plus L. Okay? Well, P1 plus L is P2. Perfect. So we want t of 1 right there. So that's it. That's basically it. If we've parameterized our line. Now t in the middle will just go along L all the way towards 1. Since L is defined as P1 minus P2, t of 0.5 will be P1 plus half of that distance. We'll move straightly along that line, no problem. Now, if you're not familiar with this vector notation, and like I said, we want two functions, we can break this out of vector notation just by putting the x and the y coordinates correctly. So, where am I? This equals, there we go, this equals, so P1 is just x1, y1, plus t is a scalar, times L is going to be, now L is P2 minus P1, so it's x2 minus x1, comma, y2 minus y1. That's it. So now we can break it out into the individual functions. X is going to be x1 plus t times x2 minus x1, and y is going to be y1 plus t times y2 minus y1. So now we can calculate any spot along that line in terms of t by using these functions. Now we can break this out, we can write it in different forms, and I'm going to quickly show you that because there's another form you might come across that is it's also popular, and I want to show you it's the same thing. So I just broke out the multiplication, and then I'm going to collect the x's. So then I'm going to have 1 minus t times x1, right? And then plus t x2. And this form is popular because what you get here is t times x2, which is my second point, and then 1 minus t x1. So at the beginning when t is 0, I get no x2 and all of x1. Bam, right? All of x1. And as t increases, my proportion that I'm using x1 blends out, and I'm blending in towards x2. And it just happens that comes straight across the line. So this is called linear interpolation, and we'll come back to that later. So parametric functions, the idea is I put a t in, I get it out. Oh, the one more thing I want to mention is this is a function for a line. It's not a function for a line segment. So we can actually go beyond those endpoints. If t is bigger than 1, we'll go that way. If t is less than 0, we can go that way. So that's no big deal. Let me show some slides. All right. So here's an example of other parametric equation. This is a circle. Give me a second. This is a circle. We can define x and t in terms of a radius, the cosine and sine of 2 pi, and you just times t to set the angle. This is a parametric equation. And we can go all the way around the circle by changing t. Now the reason this looks chunky and not like a real circle is simply because they only chose 20 points of t along the line. If you want the circle to look more nice, you can choose more points of t. Here's another example. You can do all kinds of funky shapes. I'm not going to bother trying to figure out the math here, but you can play with these parameters, just change the t, and as you change t, you get these really cool shapes. This was very popular in early video games to get really complex looking movements. A sphere is the same thing. We can do all the math, we can figure out the parametric function, and instead of t, because the sphere is in 2 dimensions, I use u and v. So as I go from u to 0 to 1 and v 0 to 1, I can get a sphere. Okay. So parametric functions, you don't need to know all the math, you just need to know the intuition. I'm just redefining a function. As I go from 0, t's at the beginning, I go to 1, t's at the end. There's one more thing I want to talk about, and that's one nice thing we can do with parametric functions. Let's put some space in there. So with parametric functions, we can do line intersections. We can calculate where 2 lines intersect. And again, I'm going to write segments in here because with graphics, we're typically dealing with line segments and not lines. And we can do that using parametric equations. So this is pretty neat. I'm going to draw it out. If I have 2 line segments, I'm going to call this line A and this line B. If we have them in parametric form, then I'm going to that's not what I wanted to do. I'm going to use this one. I'm going to extend them out just so you see that they're actually lines. What we do is we solve for 2 quantities here. We solve for TA, and that is what t value in the line segment of A did we hit B? Where did they hit? And we also solve for TB. So where along A are we and where along B are we? In this case, you can see they don't intersect, but the rule is really simple. If both TA and TB is between 0 and 1, because that's how we defined our parameterization, if it's both in the main line segment, then we have an intersection. Cool. In this case here, TA looks to be within 0 to 1. Awesome. We're right in the middle of TA where they match, right there. However, TB is probably less than 0 or bigger than 1, depending which way you arrange the line. So it didn't hit, it hit B will hit A, but not within that line segment. So therefore, we have no intersection. Okay, therefore we have no intersection. And I'll just quickly show a slide on that. Let's change over. Awesome. So here's the math. I'm not going to get into it. You can derive it if you want. But what we do here is you can determine A and A and B parametrically. Okay, and then this is a version I've already shown you. And then you basically set them equal. When are they equal? You can calculate that. When they're equal along TA, this equation will tell you where it is along the line of A. This very similar equation will tell you where it is along line B. So you can look it up. I'm not going to derive it for you, but it's actually really simple using parametric forms to find out if 2 lines intersect intersect or not. Okay, and I think that's it. Yep, that's it for our parametric. So we'll come back to this. You'll see this come up again and again, both parametric equations and line-line intersections. So this is actually pretty challenging for people that aren't that mathy. So put this video aside and maybe come back and review it again and again later when it comes up in the notes. So when I say something like, oh yeah, this is a parametric form, go back and watch this video again to remind yourself. Or if I say line intersections, you can do that, right? Come back and look at it again and you can see how difficult or not that it is. Thanks.